Why is Kriging Interpolation not as good as we thought? The Kriging technique provides models to smooth. These models may not honor the original data distribution. Also, it may not honor the spatial structure of the original data. Be prepared to understand all these concepts and more in today's video tutorial. Hello and welcome back to the Conditional Gaussian simulation course. This is the third lesson of the course, and today we are going to be analyzing why Kriging Interpolation is not good. Let's start. Remember that if you want to have full access to all the content, just go to the GeoRGB community website at gscourse.online. Then get enrolled at the Conditional Gaussian simulation course for environmental projects. Then you will be ready to start learning. And as you can see, we have already loaded several lessons for this course. We have the introduction, we have the lesson 1, that is the Gaussian anamorphosis, we have the lesson 2, that is simple Kriging, and for today's lesson, we are be working on lesson number 3, that is the Kriging model analysis. Also here you can download the scripts that we are using during the lesson. Also you have the option of watching the lessons through the GeoRGB community YouTube channel, but here in YouTube there are some restrictions. In the previous lesson we was working with the Meuse River dataset, that is a dataset related to contaminated soils, and we was working with the zinc concentration. We was using the simple Kriging technique in order to create a prediction map related to the zinc concentration for those unsampled locations. Before of using the Kriging technique, we was doing the exploratory data analysis, and what we saw is that the data didn't follow a normal distribution. Even we saw several outliers due to the high values of the zinc concentration. Then we decided to use the Gaussian anamorphosis technique to transform the original data in a new variable where the data is showing a perfect normal distribution with a mean of 0 and a standard deviation of 1. Then we pass from this original data to a new variable where the data is showing a perfect Gaussian distribution. We was using this data, that is the data that we designated as a step number 1, this data over here, that has the Gaussian anamorphosis transformation. Then with this data, we created the prediction map and the variance map. The variance map is the map of the error. At the end, we took the prediction map and we did the reverse transformation in order to have the values in the original scale. And the result was this map over here. Now we are going to analyze the variance of the original prediction map. This map is the map that we created with the Gaussian anamorphosis. Is this map over here. But first, let's go to do a very short explanation about the relation between the dataset and the model. Let's go to imagine that we have the dataset. This dataset is the black dogs. Then we are going to create just a cross-section. I'm going to create now the model with the red line. Then as a simple Kriging is an exact interpolator, the model passes through the dataset, like this one. And if we are taking as an example that the dataset is the zinc concentration, what we can see is when we pass from one zinc concentration to the next zinc concentration, the transition is pretty smooth. Here we have a value, for example, of 100 ppm, and here we have a 200 ppm, And we can see that when we pass from 100 to 200, this transition is pretty smooth. The same happens when we pass from high value to a low value. This transition is pretty smooth. And this kind of transition from one data point to the next data point, it's not pretty realistic, because the reality is going to be something like this. This one is more real. It happens the same because we pass from high value to low value, but it's doing something like that. The variability is bigger than the one is showing by simple Kriging. And it happens because one of the assumptions that we are doing when we are using the Kriging interpolator. And that assumption is to minimize as possible the variance, to make the variance as minimal as possible. And that's the error of the variance, right? We want that the prediction at the location minus the real value in that location to be minimal. As we minimize these differences, we are creating a model that is pretty smooth. And that is what we are going to see now on the map that we created the other day, on this map. Then we can use this plugin, the Terrain Profile. If you don't have that plugin, you can go here, manage and install plugins, and look for that plugin. And then you can install the plugin. Then click to use that one. Select the layer that you want to add to the canvas. Then add. In this case, we are going to add the model, and also we are going to add the data set. The data set in this case is step 1. Then we are going to add this one also, but we have to select the variable that we want to see. That is going to be the Gaussian transformation. Then OK, and now I'm going to change the color for this one for a black one. And also I'm going to change the buffer. Here the buffer is going to be 10. And that's good. And now we can make ascension of the model. Then, for example, let's go to use several data points to create the section. Then just click on the map to create the line, and we are going to use the data points. We are going to take some of them to see what's going on with the model and with the data set. Double click to finish, and what we can see here is the red line is the model, is a section of the model, and the black line is the data set. The data set is just a point. Even here we can see a line, it's just a point. Every time this black line changes the direction is because we have a sample. And the first thing that we can see is that the black line with the red line, it doesn't match. As I said previously, the simple Kriging and the ordinary Kriging, there are exact interpolators. And as we saw here, we said that the model has to pass through the points, but it doesn't happen most of the time because of the structure of the data. That's in an ideal scenario. In an ideal scenario where we have no nugget effect, that the structure is pretty good, then we are going to have the model that pass exactly through the data set. But in most of the cases, never is going to happen, right? But it's pretty close to the data. But also we can see here how the smooth is the simple Kriging model. As I said previously, when we change from one concentration to the next one, the red line is pretty smooth. Here is pretty clear how it passed from this data point to the next one data point, and it's pretty smooth. There is very little variability on the transition from one data point to the next one. Even here is pretty evident. From this data point to the next one, the transition is pretty smooth. Also, we are going to see that the simple Kriging model doesn't honor the data distribution. We are going to compare now the histogram from the original data, from this data over here, with the histogram that we get after doing the simple Kriging model. Then let's go to look for the scripts. I'm going to use this one here, and it's going to be this one over here. Then first we are going to do with the original data. That's the step number 1. The parameter is going to be the Gaussian transformation. Label X is going to be the zinc concentration, but remember that in this case is the Gaussian anamorphosis transformation. The label Y is going to be the number of samples. Title of the graph is going to be histogram. Subtitle is going to be Gaussian anamorphosis. The minimum value is the one we can get here at the attribute table, minimum and maximum. The minimum is this one. We can copy from here and paste over here. And maximum, have too many windows open. Maximum is this one, copy, and I'm going to paste over here. Paste. And the number of bins is going to be 12. That is the root square of 155 samples. Then I'm going to add the labels, but I'm going to pass the video faster. I already added all the labels. Now I'm going to save this file. Simulation is going to be this folder over here. And I'm going to save this one as a original Gaussian anamorphosis. Save. And now we can run this script. Double click to open. And this one is the histogram for the Gaussian anamorphosis transformation from the original data. Remember that this is a new variable. We explained at the previous video how it works. The next step is to create the histogram, but for the simple Kriging model. That one is step number 2. Remember that with step number 2, we have all the grid points. For each point, we have a value. Then we go here again. Now select step number 2. Select the variable, is this one. The parameters are going to be the same. The things are going to change is the limits, the maximum and the minimum. Then go to the attribute table, select the minimum, and we are going to do the same as we did before. Paste here the minimum, look for the maximum, use this one here, copy, paste here the maximum. I'm going to change the title here. I'm going to add simple Kriging, and the rest of the things are going to be the same. Then we can save again, but here is going to be simple Kriging. Then save and run. We can open. The first thing it called my attention is the number of samples that we have for each bin. In this case, as you can see, they are very big compared with the other one. But you have to understand that in this case, we have 155 samples. And in this case, let me check. We can check here. We have 3,000 something. 3,153. That's the unsampled locations that we have here. Let me close this one. At the raster, we have 3,153 unsampled locations. There is all these points that we can see here. But for the other one, we have the yellow ones, right? Well, this one is a different color because the yellow one is for the Muse River dataset, and this one is for the transform data. We have 155 samples. At the end, the values that we have in the step 2, for example, if we select this layer and go to information and we select this point over here, you are going to see that the value here is 0.07. But if we select the raster, is this one, and now we select the pixel, we're going to have the same value because the point and the value that we have at the pixel is the same. The next thing it called my attention is the shape. As you can see here, the shape is a perfect bell, but here is not that perfect shape, right? It's a little bit different. We have this peak over here. Another difference is related with the mean value and the median value. Here we have a value of 0, but here the value is not 0. Another difference is the standard deviation. In this case we have 1, but in this case we have 0.86. And also the limits are a little bit different. Then we can see that after applying the simple Kriging technique, the results that we get on the model are not the same as the original data that we used to create that model. Then we can say that the simple Kriging doesn't honor the data distribution of the original data. That is the data that it comes from the Gaussian anamorphosis. Now we can see how the simple Kriging also doesn't honor the spatial structure of the original data. We are going to see that after applying the Kriging technique, the results that we get are different. To see that one, we are going to use the script number 19.2. That is the model semivariogram omnidirectional. Then double click. First, we are going to select the step 1 because we want to see how it is on the original data. The cutoff is, we was already explaining these variables at the previous lesson. Then if you want to know about it, just check that lesson. The cutoff is going to be 1250. The lag is going to be 100 meters. The partial seal, the range, and the inaccurate effect, these ones are values that could be an approximation because the script is going to fit the model automatically, okay? In this case, it's going to be 1.2. Even here is saying seal, that's wrong. This one is the partial seal. The model is the spherical one. The range, we can add here 1300. The inaccurate effect 0.1. Label X is going to be the lag distance in meters. Label Y is going to be the semi-variance. Title of the graph is a spherical model for the zinc concentration. And subtitle is going to be Gaussian anamorphosis transformation. Remember that these values, the cutoff and the lag distance, they are important and we have to keep the same values as we put for the exploratory data analysis when we was doing the semivariogram, because this, as we change these values, the model are going to be different, okay? Then I'm going to add the labels, but I'm going to pass the video faster. Here we have the values for the model. We have an inaccurate effect of 0.10. We have the spherical model, we have the partial seal at 1.29, and we have a range of 1176. The distance are in meters. Then we can open, and this one is the model for the original data based on the Gaussian anamorphosis. Now we are going to do the same, but for the results that we get on the Kriging model. Then here we have to select step number 2, select here this variable, and here I'm going to put simple Kriging, and I'm going to save with a different name. That is going to be this one, but here simple Kriging. And now I can run this one. Now here we have different information. We have negative effect, 0, no negative effect. Spherical model, and the partial seal is 1.3, and the range is 1876. Now we can open here, and we can see that the model doesn't fit really well. We compare with the other one, here it fits perfect, but here it doesn't fit really well. Then we have to make some modifications on the cutoff to have a better model here. Then that's the first difference that we can find between these two. That here the model fits really well, but if we keep the same parameters, the model doesn't fit well. Then we have to modify some things. Then let's go here and change here the range. I mean, not the range, the cutoff, this value over here. Because as you can see, the range is pretty large here. Then we have to add more cutoff. Let's go to try a value of, I don't know, 1400, something like that. And let's see what happens. Then we can run again. Now we have these values over here. Again, negative 0, partial seal is 1.01, and range is 1400. Now let's go to see if it's good fit. That one is better, but the fit is not like this one, right? That it fits really well on the data. Here we have some data points over here. Fits well at the beginning of the graph. That is the most important part of the graph, right? Is when we have the highest correlation between the samples. But the fit can improve a lot. Even we can try in this case to fit the spherical model manually to see if we have better results than the automatic fit. But to fit the model is not part of this exercise. The part of this exercise is to see the differences between the original data and the data that we get with the Kriging model. Then we can see here that they are different models. Then we can say that the Kriging technique doesn't honor the spatial structure of the original data. Because here in the original data, we have a seal that is the summation of the negative effect plus the partial seal. In this case, it's going to be around 1.4. But after applying the Kriging model, what we can see is that now the seal, that is the negative plus the partial seal, is 1. Then we lose 0.4 of the variability of the model. Then the results that we get again with the simple Kriging model has less variability than the original data. Then we are losing variance on the model. Also, the range is a little bit different. But the most interesting thing, as we can see on the graph, is the seal, right? The seal, the maximum value is here, and it's around 1. And the range could be also approximately over here, right? Because, as you can see. But here, what we can see is that the seal is around 1.4. An additional limitation of the Kriging technique is that it doesn't tell us about the model's uncertainty. The error map shows how accurate the estimation is, but it doesn't give us any clues about the most probable range of values at the unsampled locations. Then the point is when we can use the Kriging technique. And my answer is we can use the Kriging technique when the density of the samples is very big. In that case, we're going to have a lot of information, and the distance between the two pairs of samples is not really big. We are not losing the variance. And also we can use Kriging when we know that the phenomenon is not showing a big variability between two data points. If we know that the variance of the phenomenon is pretty constant in all the area, then we can use also ordinary Kriging. I say ordinary Kriging because in ordinary Kriging, we know that the mean is constant in all the area, but we don't know the value of that mean. However, when we are using simple Kriging, we are assuming that the mean value is constant in all the area, but also we know that value. Then what happens when we are using simple Kriging is that the models converge towards the mean value in those locations where we don't have any sample. But in ordinary Kriging, what we are taking is the mean value of the local data. Because as we don't know what is the mean value, we are taking the value of the local data. In that case, the ordinary Kriging is more flexible. And simple Kriging is not very realistic, right? Because as I said, if we are not having any sample, what the model is going to do is to converge to the mean value that we indicated. And we are assuming the same mean value for all the entire area. And then the model loses a lot of flexibility. While in ordinary Kriging, the model can adapt to the local mean value associated with the samples closest to the unsampled location. To finalize today's lesson, let's go to see a slide summaries that I created. First point, model smoothing. Kriging tends to smooth estimates, which means it can lose detail in the area of high variability. This may affect the accuracy of the predictions and result in a less realistic representation of the phenomenon under study. Second point, not honoring original data distribution. Kriging doesn't guarantee that generated estimates will maintain the distribution of the original data. This can lead to an incorrect interpretation of the statistics characteristics of the phenomenon in question. Third point, not honoring original data structure. Similar to the previous point, Kriging may not preserve the original spatial structure of the data. This can result in an inaccurate representation of the variability and spatial correlation present in the original dataset. Fourth point, loss of variability. As a consequence of the previous points, Kriging can lead to a loss of variability in the estimates, negatively impacting the quality and accuracy of the model predictions. Fifth point, no direct uncertainty information. While Kriging provides an error variance map useful for evaluating estimates accuracy, it doesn't offer direct information about the uncertainty associated with the estimates themselves. The error variance informs us about the dispersion of the estimate errors, but doesn't reveal the range of possible values and their likelihood of occurrence at each location. This lack of uncertainty information can be problematic in applications where it is crucial to account for estimate uncertainty, such as risk-based decision-making. The absence of this information may lead to an incomplete interpretation of the phenomenon under studying and suboptimal decisions. In such cases, alternative modeling approaches like conditional stochastic simulation, which generates multiple possible realizations of the phenomenon under study and provides a measure of the associated uncertainty, may be preferable. That is the reason why in the next lesson we'll introduce conditional Gaussian simulation using QGIS. Then thank you very much for watching this video and see you on the next lesson.